three levels for predictor like this one: ethnic, African, Asian, and Caucasian. You can use something like this: 1-0 as African, 0-1 Asian, and 0-0 Caucasian, something like this. So you transform one categorical predictor to two dummy variables. This x1, x2, they are called dummy variables. Okay. So in general, linear regression can be applied to both numeric and categorical predictors, but we use categorical predictors, we have to translate them into dummy variables. Just put this into the model as the usual numeric variables. Now, so we have assessed the quality of fit. The next question is, how do you know if your linear model is appropriate? Okay. How do you know if your model is actually linear? Okay. So we have talked about what variables we should put in the model. We assume that we are given those predictors, but later we will talk how to select predictors in the model. But right now, let's say you have a set of predictors and you fit the model. How do you know if your model, your linear model, y equals beta 0 plus beta 1, x1, beta 2, x2 is appropriate? So your model is appropriate if the error has a normal distribution. Okay. So you see that because y is beta 0 plus beta 1 x1 beta 2 x2 plus some random error. So if you want to check your model is appropriate, is linear, model is correct, is the right thing to go, you have to check if this residual actual observation subtract the predicted value follow the normal distribution with zero mean variance sigma squared. Now you have three things to check. First, this error has a normal distribution. Okay, EI has a normal distribution. Or normality assumption. You can use the QQ plot. QQ plot that we discussed last 2 weeks. Yes, to check if your residual has the normal distribution, or you can do histogram. If your histogram is symmetric, okay, then can believe that is normal. The second thing is this observation EI, because one residual comes from one predicted response. Right? These residuals must be independent in the sense that you plot the sequence of residuals they should have some kind of trend. Or you plot the trend residual with the predicted value, you should see some kind of trend in your plot. That is, there should be some correlation between error with EI and predicted value. And third thing is constant variance is sigma squared. You can check by plot the variation of residuals against the predicted value and individual predictor xi. If you have constant variance sigma squared, then the variation of the residual shouldn't change with the value of different predictors. Then this one. So this one is a plot of residuals E1, E2, E3. So this one is a sequence. This is the first residual for first observation, second observation, and so on. And this is the value of residual. If your residuals are independent, then you should randomly spread around the graph. No correlation in the pattern, no trend or whatever. This is the check for independent. This is a check for normal distribution. So you do the QQ plot one time of normal distribution and sample one time. So it's good for straight line. Okay. straight line. So that's quite straight, but it's okay. It's not that different from normal distribution. So normal assumption is acceptable here. This, okay, by the way, this error, so you can normalize the variance. This error to have variance 1. So this error term has normal distribution with 0 mean and variance sigma squared. You can normalize this to 1 by dividing this term by the sample standard deviation of this error. So the sample standard deviation of this error is given by this one, square root of mean square error divided by this degree of freedom n minus p minus 1. So this is the estimation of sample standard deviation of the residual of this term. So the error divided by sample standard deviation of error is as a normal distribution. And this term is called standardized residual. So many software plot the standardized residual. They show standardized residual, not the actual residual distribution. This one. So this is the plot of residuals, standardized residual against the fitted value y. So you shouldn't see any trend randomly spread around the graph. So it means the error independence of the EI, the residuals are independent. And this is a plot of residuals against the predictor X. You shouldn't see any trend either. And randomly, variation is kind of constant for all value of X. So we can assume that they have constant variance as well. Now, this predictor, this coefficient beta is a function of x and y in response and predictor x. This x from our model, this x is a scalar of numeric variables. Okay, it's a deterministic variables on the model, but this y. This one is not. This one is actually is a random variable, right? Because it's a deterministic term plus normal distribution. So y actually has a normal distribution, but x, this term x is deterministic. So when you estimate this coefficient beta, so beta is a function of x. Okay, x. This term x is a metric of scalar, right? But this y. This one actually is a random variable. Okay. So this beta will turn out to be a random variable as well, or the estimator like sample mean or something like that. Okay. So this beta is a random variable. So you can study the property of beta. Study the property. You can do hypothesis testing on the value of beta. The key results, okay, I'm not going to prove. The key result is here. First, if you take expectation of your beta is this one. So beta is a vector. It's a vector of use underscore to represent the bold character because I cannot write the bold character on screen. So I just use this bar to represent the vector. So the expectation of this vector x beta will be equal to the actual coefficient. So this is similar to the expectation of x bar equals to mean, right? So if you take sample mean of the population, this expectation is population mean of unknown constant. Same here, expectation of this beta estimator beta hat is the actual coefficient of the model. This is a property of this estimator. And the covariance of this matrix beta, this vector beta, is given by this one. Covariance. So covariant matrix. Covariant matrix is the matrix P by P. Where entry is covariance of beta. Entry in this matrix is covariance beta. This one is P by P. Because beta hat is a random vector, the covariance of the random vector is a square matrix, where element ij is the covariance of beta I and beta j. This one. And it's given by this equation, sigma square. So this one is an unknown constant, sigma square, and the residual variance of the model multiplied by x transpose x equals. This is the property of the estimator. And this individual beta, each individual beta is the random variable, is the estimator. It has a property that it is a normal distribution. So this is the mean of beta, mean of metric beta. So expectation of beta hat is beta. But the actual distribution of the estimator beta I has a normal distribution with mean beta I. So this is unknown constant. And variance is CII multiplied by sigma squared. This CII is the diagonal element of this matrix x transpose x equals. So if you this one, this is x transpose, this matrix is x transpose x equals. The diagonal element, this one, and this one. This is C00, C11, and C22. Okay. This is the big. Because this one is the x transpose x equals. This one is the inverse of this one. Diagonal element is this one. C00, C11, C22. So the variance of so beta I hat, this estimator, this coefficient has a normal distribution with the mean beta I and the constant, the actual coefficient which is unknown, and variance CII times sigma squared. Sigma squared is also unknown. It's a residual variance. So from this, this is a proof. You can just skip this one. Okay. And use this one. We use this result later. The sum of square error divided by error variance. This one has a chi-square distribution with n minus p minus 1 degree of freedom. This is the first result. And the second result is the expectation of sum of square error divided by n minus p minus 1. This term is called the mean square error. This whole thing. Because you divided by SSE divided by n minus p minus 1. This term is called the mean square error, MSE. This term, expectation of this term is equal to sigma squared. So if you want to estimate the error variance, sigma squared, you can take sum of square, FSE, this one. This term is your SSE. Y subtract y hat squared. This one is SSE. If you divide this term by n minus p minus 1, it will be the estimate of the error variance sigma squared. Okay. So this is two key results. Now, this is one. Okay, this is the first one. Beta I have estimator of coefficient has normal distribution with the actual coefficient value and this variance CII sigma squared. And this sum of square error divided by sigma squared as a chi-square distribution, and expectation of mean square error is sigma squared, and three key results. Now, let's say you want to find the mean response, the predicted confidence interval on the mean response. So you can, if you plug in x into the equation, you get the predicted mean response. But you can also find what the confidence interval for the mean response, similar to the confidence interval of the mean. So you can see that if you have different data set, similar concept to sample mean, if you fit different data set into the equation, into the model, you will get different value of beta, right? Because for different x, to compute x transpose matrix y, you get different value of beta. So different data sets give you different beta. Okay. So the question is, how close it is for the point value of x? How close is this that the predict mean response close to the true mean of the model? So we can answer this question by using the confidence interval. So we use the knowledge that individual with beta 0, beta 1, beta 2 has a normal distribution. And individual beta hat, they are normal. So if you sum p plus 1 normal distribution, normal random variable, you still get normal random variables. Should I go? Okay, should go to this one. Okay. This will have, is the sum of p plus 1 predictors. Okay. So this itself is a random variable with this mean. You take expectation with what? because the expectation of beta n is beta. If you take the mean of this whole equation, you get beta 0 plus beta 1. And this is the sum of normal random variable. So if you subtract this one by mean, by its mean divided by the sample standard deviation, subtract mu hat by mu divided by the standard deviation of this. This standard deviation of this is given by this one, made with sigma times square root x transpose. This one is the x that you want to predict. This small x. Okay. This capital X is the matrix that from the data that you use to fit the model. And this x is the value of predictors where that you want to predict the value of y. Small x is the observations where you want to predict the new value of y. New observation, and this x, capital X, this is a matrix that comes from the data set that you use to fit the model. So if you replace this sigma by this sample standard deviation S, so we know from this result that you can replace, you can use this one as the estimate of sigma. The square root of this one is the, you can use it to estimate sigma here. So this whole thing has a t distribution with n minus p minus 1 degree of freedom. So this n minus p minus 1 is this term. Okay, this one. So this whole thing has a t distribution with n minus p minus 1 degree of freedom. So the confidence interval on this one predicted mean response. So it's given by this one. Subtract plus minus the scale, this scale term multiplied by this error term. So this whole thing. So you can think of this whole thing as one standard deviation, which is this term, plus some multiplied by some scale value, plus minus the predicted mean. So this whole thing is your confidence interval for the predicted mean response. For this data set, this is your y, this is your x1 and x2. This is your x, and this is your x. This is your x, and sorry, this is your y, hardness, and this is the your x1 copper content, and this is the annealing temperature, the temperature that you use in the manufacturing process of the steel. This is y, x1 and x. Okay. So this question asks you to estimate the y at x1 equals to 1.5 and y x2 equals to 1,150 or 1.15. This unit is 1,000. As you do confidence, estimate the confidence interval of y predicted mean at this value of x. So you fit the request, you just plug in. So your x the observation x is your observation x is 1.5 and 1.15. X transpose is this, and this S is square root of FSE and minus P minus 1. N is is 10 and P is 2. And this SSE is summation of y subtract y. This S. Okay. So you have to fit the regression model on this data first. This is y, x1, x2. And fit the regression model and find out what is the sum of square error. This one, to find this one. And your metric x, is y02, y03, y02, and y05, y2, and y1. Good, x. So just compute x transpose inverse, multiply by x small x transpose, and multiply by x. So this whole thing is scalar. After you multiply all the vector and matrices, this one will be scalar. X square root multiply by this one, and multiply by this critical value. You get the confidence interval on the printed mean. So this mu hat, this is the mean response given in observation x. So you just plug in this value of x into the regression model. Plus minus this term. So this is the result. You plug in x1, 1.5, and x2, 1.15 into this equation model. You will get 69.826, and these two terms, and critical value multiplied by this whole standard deviation or standard error, you get 4.083. So this is a confidence interval on the mean response. What about the prediction interval? This is the confidence interval on the mean. You want to find the confidence interval on the response itself. Response itself, y. Y has a normal distribution. Okay. Y itself has a normal distribution with this mean and variance sigma squared. Because the model is y equals to summation of beta I plus epsilon. Right? So response y itself is normal with this mean and this variance sigma squared. This one and this one. Okay. This one, okay, this one is predicted mean response, okay, and this one, okay, and this mean, okay, this one and this mean. You subtract this one out of this one, you will get a normal distribution with zero mean, and the variance will be the sum, sigma squared, will be the sum of this variance and the sum of this variance. The sum of this variance is this one. this one, okay. This one, the variance of x beta hat. So you get sigma square plus sigma square x plus this whole thing. So you take sigma square out, so you get this thing. So this term has this normal distribution with zero mean and this variance. If you divide this term by this variance, you will get the normal 0, 1 standard normal distribution. If you place this sigma by the sample standard deviation and the estimate of standard of error variance, you will get a t distribution. This one becomes a t distribution with n minus t minus 1 degree of freedom. So from this, the confidence interval on the single response, confidence interval in the single response, is given by the estimated response, plus this critical value and this s multiplied by this value. This is the equation for prediction. The confidence interval for the single response is called the prediction interval. But this one is the confidence interval on the predicted mean response. It's not the same. This one is for mean confidence interval for the mean response. But this one is confidence interval for single response, single y. But the previous equation is for the mean response. So this you just plug in value of s and observation x bar and this data that you use to fit the model. This example, let's go back and work out at home. So you fit the regression model and plug in the value of s and value of x transpose and x observation x bar. In this case, your x is this data x1. X1 is 1.5, X2 is 17, X1 is 1.5, X2 is. So for this data, single mean response for X1 1.5 and X2 equal to 17. And this is the prediction confidence interval on the mean, and this is the confidence interval on the prediction interval. In practice, you just apply as plug-in value into this equation, and nothing more than that. It's really straightforward. Now, usually people will be more interested on this one, the test of the regression model. The question that people usually ask when you fit the regression model is that, is your regression model is better than using the average? So if your model predicts no better than the average, then there is no need to fit the regression model. If you use the average value, and it will be much the same result as your prediction. Your regression model, then you don't need to fit the regression. So the hypothesis testing on whether the model is significant. So when you say the model is significant, it means one of the coefficient is not zero. So your model is y equals beta 0 plus say beta 1 x1. If the average of the data is as good as the regression model, it means these two terms will be 0. That is, your model predict a constant. You use average to predict y. That is, beta 1 and beta 2 are 0. So your hypothesis for significance of the regression model is beta I is 0 for I from 1 to p. You have three predictors. If your model is not significant, meaning that the average is as good as your model, then beta I is 0. I goes from 1 to p. So you have to leave beta 0 as the average. The alternative hypothesis is at least one of the coefficients is not 0. If you do not reject the null hypothesis, then you can use the average to predict the value of y and don't need to do regression. That is when you fit your model to noise. You know what noise? Noise is a random value. If you fit your model to noise, then this null hypothesis should be true. You use the average is as good as the regression model. So if your null hypothesis is true, this is the property when this one is true. If all the beta I are 0, the sum of square regression divided by sigma square, you have a chi-square distribution with p degree of freedom. Okay. So you can test, you can do this kind of test statistic. This is chi-square divided by its degree of freedom. This is the chi-square divided by its degree of freedom. This one, our property is SSE divided by sigma square is chi-square. So if you divide this one over n minus p minus 1, you form this ratio and you get an F distribution. So this thing is just a mean square equation, sigma square. SSR divided by p is called mean square equation. SSE divided by n minus p minus 1 is a mean square error because sigma square cancel out. This one has an F distribution with this p degree of freedom and n minus p minus 1. This one. So you can, this test it looks pretty much like the ANOVA table. It's called the ANOVA table for regression model. So you have the source of variation is a regression, and sum of square is sum of square regression divided by p degree of freedom, and you have the mean square as LSR divided by p, and error sum mean square error is LSD divided by n minus p minus 1. And if you divide MSR by MSD, you have a test statistic F0, and you compare it with the F distribution with p n minus p minus 1 degree of freedom. So you can use a software if you use software, application software, it will show this table to you, like this one. In Python, you can use this one, set audio module, and use this one, function OLS, ordinary bit square, x, y, and x dot fit, and you print the model summary. So this, okay, this is a code to compute the significant test for the regression model. And you can use this one, function OLS, to do the model fitting. It gives you the R square and F statistic. This one, just look at this one. This one is the F statistic from this equation. MSR divided by MSE. And this one is the p value. P value of this test statistic 4.1 to the minus 8. So this means you reject the null hypothesis. So if this one of the coefficient is not 0, so your regression model is significant. So in the exam, you can bring your calculator, but you should be able to compute. So on the first, you should be able to compute to fit the model and compute this term, SS Sum square equation, SSE, something like that. If you don't know how to use Python, you have to do manually SSI, SSE. SSI is this one. This one. SSI is summation of y predicted value subtract y bar. The data set in Excel will not be large, like few entries, 5, 6 values, probably 2 predictors, something like that. Let me stop here. So this format, I try to work out some number here. You can work out one example. Just check your answer with this one to make sure you understand how to plug in equations. But usually the software will use for you in Excel. If you cannot use software, you should be able to plug in numbers to equations to make prediction.